Hello, I'm Dr. Anne Nortcliffe at Canterbury Christ Church University and the Head of Engineering, Technology and Design. My challenge that I'm setting you is, can you make your rocket go higher than mine? So what resources are you going to need? Well, they are things that you can find around the home. Paper card, canister, so like a spice bottle canister with a pop-off lid or a film canister with a pop-off lid, vinegar and bicarbonated soda, but if you haven't got vinegar and bicarbonated soda, baking powder and water is just as good, but I had baking powder and balsamic vinegar. Any old vinegar will do, so malt vinegar, white vinegar, wine vinegar can be used. You need scissors, ruler, pen and pencil, teaspoon and PVA glue. So how much rocket fuel does your rocket going to need? Well, I found that what was ideal was about 1 to 2 millimeters of vinegar in the base of the canister. Now I use balsamic vinegar because that was the only vinegar I got in the house, but you can use malt vinegar, you can use white vinegar, and as I've said earlier, you can use baking powder instead of bicarbonated soda, which actually has the dry powder ingredients of the alkaline and the acid already in powder form, and then you're just adding water to make it acid and alkaline to then get the chemical reaction. Whereas I've used bicarbonated soda and vinegar. And you need about 1/4 teaspoon of bicarbonated soda placed in the lid, and then you put the lid carefully snapped onto the canister and place the lid onto the base down and wait for it to chemically react and the canister will pop off. But what else does your rocket need? Well, you're going to need to make, using the cardboard and paper, rocket fins and rocket nose cone to help the aerodynamics of the rocket. So this is my first attempt using paper, 3 fins and a very long elongated nose cone. Let's see how it does. So that was the first attempt. Now for my second attempt, this time made with red cardboard, more aerodynamic fins and a more shorter nose cone. Unfortunately the weather conditions had changed, so where it was sunnier previously when I did them with white paper, for the cardboard it's gone colder because it's rained, which would show, as you can see, the time delay on it, the rocket taking off, would indicate that you actually need a little bit of heat for the vinegar and the bicarbonated soda to react, which means that it's an endothermic chemical reaction. So how successful were the 2 different rockets? As you can see, the red rocket only actually managed to go up 21 bricks, whereas the white rocket, with a much more elongated aerodynamic nose cone, managed to do 23 bricks. Each of the bricks and a bit of grout measures approximately about 7 centimeters, so you can see the red rocket actually achieved a trajectory of 147 centimeters, whereas the white rocket only achieved a trajectory of the white rocket achieved a trajectory of 161 centimeters. So you can see, let's see if your rocket achieve higher trajectory. Though the white rocket achieved greater height than the red rocket, how ethical was that experiment? You know, how was it a fair test? 1, white paper can weigh less than the red card. 2, I was pouring in the vinegar and only measuring by eye. A more precise measure would be to actually draw and measure the exact amount of vinegar each time, and the same with weighing the amount of bicarbonated soda, but also the design of the rocket, making sure the paper and the cardboard that's used is identical in weight. So you're experimentally measuring like for like, but also ethically the experiment should have been repeated again and again and again to get that statistical analysis to see, you know, that it is correct, but also mark the same spot off for the takeoff, so you actually measuring consistently the same each time to actually make a true comparison which is the better rocket. Now you can investigate further your trajectory of your rocket using free software like this, which is physics tracker software, which is open source, which you can install on your computer, and you can import your video or film of your rocket and then plot the trajectory of your rocket at each point, and that shows all this real-time data of your rocket trajectory. And then you can actually apply some mathematics to find out what is the velocity on going up and what is the velocity going down. So using the tracker software, we can actually calculate the rocket velocities. So how do we achieve that? Well, we use this equation here, which is actually computing. You need to compute the difference in the distance travelled. In this case, the distance travelled is the y-axis because it's going up, and divided by the difference in time that's to achieve that distance travelled. So I've selected the point it reached in height, 1.38, minus the height when it left from the ground, which this number here is approximately 0, which is actually why we were saying it's up from the ground, and the difference in time divided by the difference in time. So it took about 0.5 seconds to achieve that height of 1.38 from the point of time of 0. So the upward velocity was 2.8 meters per second. The downwards velocity, in this case, we're travelling down. I've taken from the height of travelling down from 1.451, so here 1.51, travelling to the height, so it's going down, so the height is decreasing to 0.611. The difference in time that's travelled this time was at 0.867 at the greater height, and the height at the time it took to the lower height was 1.223, but because it's travelling down, notice it's negative this time. The downward velocity is 2.3 meters per second, so it's actually slower. The rocket was going up much faster and came down slower. What engineering can you learn from making a rocket canister? So what we've learned today is that with nose cones designs and the fins, we're actually learning aerodynamics and pushing the air out of the way as the rocket takes off. Experimenting and designing your different nose cones and your fins is engineering design cycle, and experimenting with different types of nose cones to see which makes the rocket go higher is really part of that engineering design life cycle. When we calculated the velocity or the trajectory of the rocket going up and the trajectory of the rocket going down, it's actually the rate of change of the distance travelled over the difference of time is actually calculus, mathematics. We also saw that the white rocket, when it took off and when it reached its maximum height, it spun round in comparison to the red rocket, if you notice carefully on the film footage, which actually is due to the fact that the white rocket had got a much longer nose cone, larger fins, which means its centre of gravity was different to that of the red rocket. So you can actually go off and learn more about computing the centre of gravity. You also saw how the rocket trajectory travelled, which actually in engineering mathematics is the harmonics of the rocket. We've also learned that experiment methods is really important if we're going to compare two different types of rocket like for like, and it's important that actually you measure accurately that you are comparing like for like, so it's a fair test. And so when you conduct your rocket experiment, you know to be have better experimental methods than I did. We saw the change in the weather conditions from the comparison to the white rocket when it was a bit sunny to when after it rained and it was a bit cooler for the red rocket, that actually the fuel, sodium bicarbonate and vinegar, when they chemically react, so the acid and the alkaline reacting, is actually a thermochemical reaction. It needs a bit of heat. It's an endothermic chemical reaction. And also, we've seen actually ideal gas laws being applied, as when sodium bicarbonate reacts with the vinegar, which is a carbolic acid, the two are reacting and producing carbon dioxide, and as they keep reacting they're producing lots and lots of carbon dioxide, which is filling up the canister until the pressure difference is so much carbon dioxide is being produced it forces the canister to separate from its lid and act as the rocket fuel going up, which is actually demonstrating ideal gas laws. So what are you going to do? Is your rocket going to be better than my rocket? I look forward to hearing from how successful your rocket is and how much more learning you do from your rockets.